Okay, I'm very, very happy to be here, and especially happy to be able to lead off with what is probably my favorite topic. It's called locality-sensitive hashing. I had nothing to do with this idea, by the way, although it was developed by some of my colleagues at Stanford, Rajiv Motwani, Pyotr Indyk, and a few other people. Just to put it in perspective, Marvin Minsky once defined a computer scientist as somebody who believes that hashing is possible. Okay, the idea that you can maintain a set of elements and find any element you want in constant time, constant expected time, but essentially constant time. That if you're not a computer scientist, you just don't believe this is possible. Well, locality-sensitive hashing is another one of these ideas where, in this case, it's finding pairs that are similar in some sense without looking at all pairs. And again, it's the kind of thing you just don't believe is possible until you've seen it. Okay? So I'm going to spend, I guess, the first 2 hours or so talking about this subject. And the first lecture really deals with what's called a very particular application of locality-sensitive hashing, which brings in all the ideas, but they're not the only manifestation of these ideas. And in the second lecture, after a short break, I will talk about some other examples that are philosophically locality-sensitive hashing, but rather different in their nature. Okay, so a little bit of administrivia before we start. First of all, these lectures, backup material is all found in this free book that we have online. The address is there, www.mmds.org. And I've put in the slide the actual sections that will cover the material that I'm going to cover. I assume everybody has access to the slides, so you can you don't have to copy this down. Now, I understand you're supposed to do homework. How many are going to do homework? Nobody. Okay. Yeah. Okay. Fine. All right. Well, if you should, I don't know, have an aneurysm or something and decide you wanted to do some homework, this is how you do it. Oh, actually, Fatima would like to, Fatima Rahimian.
So if you want to do the homeworks, there are questions already prepared on a tool called Gradients, so the link is over there. So you need to create an account for yourself. And when you have this account, you register for the course, and the code for the course is over there.
You have it in your.
Because you have it in the slides, and the slides in the screen page. And then you can see, and of course, for each question, you can actually have several attempts to get the correct answer. Every time you try, you will get a different set of choices. Okay, so you can try every question several times. And then we are able to actually give you some grades based on the results you have, if you need
and
any
of course,
grade.
if you do it, you'll get extra grades in the final. This is like a bonus.
Oh, okay.
So your bonus will not be only based on this business report you are going to have, but a little bit more.
Okay. Well, I'm going to leave this to the management of this of the school, but at any rate, I do invite you to try out the material. Okay. So everybody thinks that big data algorithms is all about machine learning. I mean, and admittedly, there is something there, no question about that. But what tends to be ignored is all of the other very interesting algorithms that have been developed specifically to deal with very large scale data processing And that's what I would like to talk to you about today. And tomorrow, and the day after that. Okay, so anyway, locality-sensitive hashing is you have a large collection of items, and you want to find those that are similar, and what similar means can be various things, but presumably there's some kind of a distance measure that determines how close two items are. If you look at every pair, you've got a quadratic process. So if you've got a million items, you've got 1 trillion pairs, or 500 billion pairs. And I don't care how many machines you have and how fast they operate, you can't really do 1 trillion things. Okay? So you've got to find some way of homing in on those similar pairs without just looking at every pair. And again, this is the magic behind locality-sensitive hashing. Again, as I said, it's a general idea. I will cover some of the generality later, but I want to focus on a very particular problem of finding textually similar documents. Okay, in general, the way locality-sensitive hashing works is you take the items and you hash them in the classical sense, that is, just throw them into randomly determined bins. But what you want to arrange, and this is the magic of it, is that if two items are similar, there's a good chance that they'll be thrown into the same bin. And if they're not similar, chances are very small that they'll be thrown into the same bin. And you're going to do this not once, but you're going to have many of the classical hash functions. And you want to arrange that, if two items are similar, they will surely or almost surely go into the same bin at least once among all these different hashings that you're doing. You get classical hashings. And if they're not similar, then the chances are good that none of the hashings will send them to the same bin. Okay, and that, of course, is the hard part. So as I said, I'm going to start with a particular problem which is both interesting in its own right, has been used in the past in exactly this way, and sort of brings out sort of all of the technology that's involved. Okay, so first of all, I said I'm going to talk about document similarity. The first thing I'm going to do is reduce it to a problem of set similarity. Okay, and again, I'll tell you exactly what it means for two sets to be similar, but roughly it means they have a lot of elements in common, so that's not a surprise. For example, you could look at web pages and think of a web page as the set of words that appear at least once on the page, and pages that have similar sets of words are likely to be about the same topic, especially if you throw away what are called stop words, the words that just appear in any document, the and whatever. You could think of, if you think of, let's say, a Netflix user as the set of movies that they liked, okay, then you can tell, you can identify Netflix users that have the same taste in movies and use one's opinion to recommend a movie to the other. Similarly, if movies are liked by the same kinds of, the same set of people or similar sets of people, then they might be the same kind of movie. Okay, and that gets you at a notion of genre of movies. I'll talk later about entity resolution. Records about people, in many situations you know that each record is about a certain person, may even have their name in it. But people's names are spelled differently, there are typos and so on. Even records about the same person will sometimes look rather different, but will presumably have some similarity. And in many cases, including one which I'll talk about in the next set of slides, you actually have to deal with this problem of sorting out which records are referring to the same person, and a set similarity gives you well, it's very helpful. Okay, so now let me talk about the problem that I want to really guide you through. Okay, so we're given a collection of documents. You can think of them as web pages if you like. And I want to find pairs of documents that have a lot of text in common. Okay, the original application of this problem was in finding mirror sites. Mirror pages are intentionally, they have the same content, but it's sort of the same content, right? For example, the mirror over here might refer to its mirror here and there and there, and the other mirrors are referring to the other mirror sites, so they look a little bit different. Or one mirror site might be sponsored by, let's say, KTH, and another is sponsored by Wikipedia or something. So that you've got it, they're not exactly the same pages, but they've got a lot of text in common. Another very interesting application which has been done is to find plagiarisms. A long time ago, I put up a page that I thought was kind of useful, and someone told me that they found a copy of that page on a site of a university, and the university had copyrighted it. Okay, and so I wrote them a nice email. It wasn't not so nice, but and then a week later, I said to myself, "Gee, I wonder if there are any more examples of this." Turned out I found 40 examples of people who've taken that same page and put it up on their own website. One person had done fantastic artwork around, but it was the same text, but the artwork was just absolutely beautiful. And I was able to do this by locality sensitive hashing. Very, very simple application. In fact, all I did was I put quotes around one sentence from the document, fed it to Google, and Google just gave me a list. It was simple as that. I'm going to talk about another application of news articles. Many newspapers put up pages with the news of the day, and if you're trying to keep track of news articles, you don't want to keep the 500 versions of the same article that appeared at 500 different news sites. You'd like to get just one representative copy of one news article. Okay, so again, working on the similar documents problem, again, I'm going to talk about three things in order. Number one is shingling. It's a simple technique which is designed to turn text strings into sets. Again, because remember, we really want to talk about finding similar sets. Then I want to talk about minhashing. And this is a technique for taking large sets of items and turning them into short signatures. And a signature in this case will be a vector of integers, perhaps 100, 200, 300 integers. And so it's a summary of a very large set, but it's done in a way that is designed so that I can look at the signatures And if I can find similar signatures, which I will do, then I can also find I will find that the sets that they came from or represent are themselves similar in the way sets are similar in the sense of having a lot of elements in common. And then I'll talk about the locality-sensitive hashing technique itself, which is the way I turn signatures, the way I focus on pairs of signatures that are similar without looking at all pairs of signatures. Okay, so again, just to summarize, documents come in, we will shingle them, the result will be a set, and in particular, think of it as the set of strings of some particular length k that appear at least once in the document. Then we'll do Minhashing, which turns the sets into these signatures, these integer vectors. And then we'll do locality-sensitive hashing itself, which will identify candidate pairs of signatures. We still need to check that the signatures are similar. Most of them, we hope, will be similar, but we still have to check them. And then, by the way, if you like, since the signatures only approximately represent the sets, we can then go back to the sets that have similar signatures and check that the sets themselves are similar. I should warn you, okay, you do have false negatives. You can have pairs of documents or sets or signatures that are similar but never get looked at. Okay. And again, by tuning this, again, the more work you do, the fewer false positives you'll have, but you can never guarantee 0 false positives. You have to be willing to tolerate that. Okay, so shingles. K-shingle is simply a sequence of K characters that appears somewhere consecutively in the document. So here, in this case, the document's 5 characters long, and I'll use k equals 2. K equals 2 is a really poor choice for shingles. You generally want to pick k large enough that the chance of any particular sequence of k characters appearing in the document is tiny. Often people pick 9 or 10. So the real k is, think of the real k as again 9 or 10. But in this case, k equals 2. So you've got AB appears consecutively, you've got BC appears, you've got CA, and you've got AB again. So the set of shingles from this document is these 3. Okay? Okay, then, okay, the set of K shingles is the representative of the document. So now we can forget about documents, we're just talking about similarity of sets. Now I claim that if documents are intuitively similar, and by this I mean textually similar, not about the same topic but using completely different words, but if they are textually similar, they will have many shingles in common. In particular, if you change a word and you're using K shingles, you can't affect anything in the set, any shingle in the set that is more than K away from the beginning or end of the word. As another example, if you know, let's say if I'm a plagiarist and I want to make it look not so similar and I move one paragraph, I'm only affecting the 2 K shingles that are at the paragraph boundaries. So here's an example. Document. The dog which chased the cat. Now that's actually wrong. It should be the dog that chased the cat. And we can talk offline if you why. Okay, but the point is, these are similar documents, obviously. But look at which and now in this case K is 3. So which shingles in the original don't appear in the in the new one? Well, it's got to at least touch which. So the first one would be G blank W. White space characters, by the way, typically count. You don't have to. You could ignore them, but typically you actually count the white space because this lets you pick up phrases consisting of two words or more in some cases. Okay, so G blank WH, WHI, and so on, and then the last one would be H blank C. Those don't appear, and then there are several shingles from the G in dog to the C in chaste. Whatever shingles you make from those will appear in the new one. So the difference in those sets is it's bigger, it's about twice as big as the change that I made to the text, but it's no worse than that. So you still will have lots of shingles in common, like capital THE, HE blank, and so on, that appear in both. So these will still have similar sets. Okay, as I said, you want to pick K to make sure that it's rare for a particular shingle to be present in a particular document. Now, on the other hand, if you pick something like K equals 9, you can get away with compressing the shingles, and the way you do just hash, let's say, character strings of length 9 to 4 bytes, 32 bits. Okay, you can do that, and you still, since documents tend to be much shorter than 2 to the 32nd characters, you still have the property that most shingles will not appear even after hashing. But this way you're compressing the shingles by a factor of a little more than 2. So it's an option. I'm not going to worry about it too much. At any rate, you can represent the document either by the set of shingles themselves or by what are called the tokens, the hashed values of those shingles. And of course, if you do hash them, then occasionally you'll have a collision where two documents appear to have a shingle in common, but they're really two different shingles that happen to hash to the same value. But again, if you're using 2 to the 32nd different hash values, chances of that happening very, very tiny. Okay, so let's talk about Minhashing now. Okay, first thing I need to do, I've never really formally defined what it means for sets to be similar. That's what's called Jaccard similarity. And then I want to talk about turning sets into these signatures, that is vectors of integers. And then that, in turn, it's easy to describe in principle how the signatures are constructed. It's kind of hard to do them in practice, so I want to do that. Okay, so the Jaccard similarity of two sets is defined here. It's the size of the intersection divided by size of the union. Okay, so here are two sets. Their intersection is of size 3, and the union is of size 8. So their Jaccard similarity is 3/8. And if you think about it, that's a pretty high similarity, right? If I picked random sets of points on a plane, I would not get that much similarity. Jaccard similarity obviously goes from 0 to 1. 0 means completely disjoint. 1 means they're the same set. Now I want to, in order to explain how Minhashing works, I'd like to start thinking of sets as Boolean matrices. Really a collection of sets. Each set is a column in this matrix. So the rows will correspond to the elements of some universal set. So, for example, if you're using K-shingles, there are only a finite number of K-shingles, so you can think of one row for each possible K-shingle. Columns, as I said, correspond to the sets, and it's a characteristic matrix. Now it says you put a 1 in the row for an element E and a column for set S, if and only if E is a member of S, otherwise you put 0 there. Okay. And then if I look at two columns, the similarity of columns is really the Jaccard similarity of the sets of rows that have 1s. Okay. And remember, since I said we want to make sure that you don't have too many, that the chances of any particular shingle appearing in the set for a document is kind of small. What this means is the matrix is sparse. It's mostly zeros. Okay, so here's a picture of two columns representing sets. And I claim that their Jaccard similarity is 2/5, so 0.4, because here's their intersection, and that's their union, right? Okay, so everybody say the intersection is where you get two 1s. The union is where you get 1 or 2 1s. Okay, so everybody okay with that? Okay, now again, I want to focus on two columns, and for each pair of columns, I can talk about 4 different kinds of rows. A type A row is one where both are 1s. And then B and C rows are those that have a 1 in one and a 0 in the other, or vice versa. And then type D rows, I have zeros in both. Again, most of the rows should be of type D. And by the way, in my examples, that will not be true because you can't really draw sparse matrices on slides. And then just to abuse the notation a little bit more, I want to use variable A to represent the number of rows of type A, and same for B, C, D. Now, by the way, the similarity of two columns is A divided by A plus B plus C, right? Because A is the size of the intersection, A plus B plus C is the size of the union. Okay. Now, to describe Minhashing, first of all, I'm going to do a large number of Minhashings. Think of it as 100 different Minhashings. And so I'm just going to describe how I would do one of them. And to describe one, I want you to imagine that I have permuted the rows, taken some random permutation of the rows. And this random permutation defines a min-hash function H. And H applied to a column is the first in the permuted order row in which that column has a 1. Okay, so it's the top 1 after permuting the rows. Then as I say, we will have many different independent hash functions, and each hash function is one component of that vector that is the signature. Okay, and I'm going to represent the signatures by another matrix where the rows correspond to the hash functions, the columns still correspond to the sets. Okay. All right, so let's take an example. Okay, here's my matrix. It's got 4 columns, 7 rows, so the 7 elements, 4 sets. Okay, so here's an example of a random permutation. Not really random, but okay. Again, the 5th row will appear first, then the 6th row is second, the 1st row is third, and so on. Okay, now, this permutation defines one row of the signature matrix, and this is what it looks like. How do I know? Well, I look first at the row that appears first. Again, I haven't actually permuted the rows of this matrix, but imagine them permuted so that this is at the top. Now I've got a 1 in the column 2 and column 4. So that's obviously the first in the permuted order of the rows. So I'll put a 1 here. This 1 corresponds to the idea that this is, again, first in the permuted order. I could have also, in some examples, in fact, if you go to the gradients homework, you'll find in some cases, I use the original row number, so I would put a 5 here and here. Doesn't matter because we're only looking for equality. The only question we're ever going to ask is equality. Doesn't matter what the actual values are, but just as long, I'm going to just, in this case, I'll use the permuted order. Now, at any rate, okay, so I got these two 1s. I still don't, since there are zeros in columns 1 and 3, I don't know what the signature values are for columns 1 and 3 yet. But when I go to the second row in the permuted order, I find 1s there. Oh, that's a really happy situation. So I'll put 2 here and here. Okay? Here's another random permutation. Now I go, again, I take the first in the permuted order. Actually, the same thing happens. The second and fourth columns have 1s, so they get the 1 from the permuted order as their signature value. Now I have to go to 2, and there's a 1 in column 1, so it gets a 2, but there's 0 in column 3, so I still don't know what this value is. I have to go to 3, and again, it gives me 1s in second and 4, but I already have, I've already resolved those numbers, so I don't change the 1s. You never change something once you've found a value. Not till I go to 4 that I finally find a 1 in column 3, so I put a 4 there. Okay. Well, here's a third example, and the result. I'll let you check that out if you like. Okay. Yeah. Okay, so here's the big deal. Okay, well, let me just state it. Okay, if I randomize the order of the rows, then the probability that the hash function coming from that permutation will assign the same value to 2 columns is exactly the similarity of those, this Jaccard similarity of those 2 columns. Well, we already know that the Jaccard similarity is A over A plus B plus C. Remember, A is the number of rows that have 2 1s. And B and C are the rows that have a 1 0 or 0 1. We went over that before. Okay, why? Okay, so what I have to show you is that the probability that the min hash values of the 2 columns is also A over A plus B plus C. Okay, so here's what I want you to imagine. Again, the rows are permuted in order, in this random order. Start at the top of the columns. Keep going down until I see a 1 in at least one of those columns. Now, the first time I see a 1, if I see 1 in both columns, then it's a type A row, and I'm going to assign the same min hash value to those columns because that's the top 1 in both of the columns. Suppose I see a 1 in this column but a 0 in the other column. Then I'll assign this row will be the min hash value of the column that has the 1, and the min hash value of the other column will be something further down, definitely not equal. That's the important thing. So what are the chances that when I first see a 1, I see 1 in both columns? That's A, the number of times that you have a 1 1 situation, divided by A plus B plus C, which is the number of times that you'll have at least 1 1. Okay? So think about it. This is important and worth thinking about. I don't know if anybody wants to ask a question at this point, but we should be sort of confident that this is that this is a real argument.
Any questions? Don't be shy. You can ask questions.
Yeah. Everybody's okay. Good. Okay. Oh, they will be quizzed. Don't worry. Okay, now, first of all, I have to tell you, when we talk about similarity of signatures, here we're not using anything as esoteric as the Jaccard similarity. I really just mean it's the fraction of the min-hash functions in which they agree. You remember the signature as columns, just ask for how many, what fraction of the components do they agree in. Okay, so what this tells you is that the expected similarity of the signatures that come from two sets is exactly the Jaccard similarity. Of course, there'll be some variance. It's just it's an expected. You're doing some number of experiments, say 100, and the expected value of each experiment is that Jaccard similarity of the sets, but they're random experiments. Obviously, the more experiments you do, the less likely it is that the similarity of the signatures will be far from the actual similarity, Jaccard similarity of the sets. But at 100 length, 100 signatures, you still got like 6-7% average standard deviation, which is not too bad. So this is a continuation of the example that I was talking about. The same matrix with the same 3 hash functions. Now, I've given you some examples of column-to-column underlying similarity. So between 1 and 3, you've got boom, boom, and boom in the intersection, and you've only got one other thing that's in the union, that's the second row. So the Jaccard similarity is 3/4, or 0.75. Now, if you look at the min-hash values of the signatures, again, 1 and 3, agree, don't agree, agree. So you've got a signature similarity of 0.67. So that's close enough. Now, again, I made up this example. There's nothing random about it, but that's sort of what you might expect. Similarly, going 2 to 4, you again have an intersection of size 3 and one more row that has a 1-0 combination. So you also again have 0.75 is the column-to-column signature. In this case, 2 to 4, they agree 100% of the time. So the estimate of the similarity is 100%. Between 1 and 2, well, they actually have an empty intersection. If you have an empty intersection, there's no way you're going to get 2 min-hash functions the same because the set there are no type A rows. So not surprisingly, you'll get 0 for both the column-to-column and signature-to-signature similarity. Okay. Okay. Now. Okay. So how do we do min-hashing? Okay, so again, think of it as a billion rows, right? That would be let's say, if my shingles are actually 4 byte tokens, there are 4 billion possible rows. Do I really want to pick a random permutation of, say, 1 to a billion? Probably not. I mean, it's a sequential process, and I'd have to store it somewhere. It's a pain. So I really like not to do that. And then if the matrix is wide, and I don't have too much main memory these days, to actually access rows in some random order, I'm often having to pull them off of disk because the matrix itself doesn't fit in main memory. So again, I really don't want to do min-hashing the way I described it, where I pick a random permutation. So what I'm actually going to do, and this is why it's called min-hashing, is because I'm going to use real hashing. And instead of, well, a couple. Let's see, instead of physically permuting the rows, I'm going to pick a hash function that hashes row numbers to some large number of values. And I'll let that value be the order in which the row appears. Now, it would be cool if the hash function were itself a permutation. It's called a perfect hash function. These things don't really exist. So I'm going to get some collisions, right, where two rows are tied. Okay. It sort of doesn't matter, really, if you think about it. First of all, what are the matrix is sparse. What are the chances in some column that both of those rows have a 1? The rows that collide. Pretty small. And if they do, okay, so you don't quite get a real permutation. Some rows get left out of the permutation. It doesn't really affect the main theorem that I just gave you about probability of same hash value, same min-hash value being Jaccard similarity. Okay, now, in order to implement this this approximation, I'm going to have to keep a matrix which essentially will eventually become the signature matrix. That is where the columns correspond to the sets and the rows are the components of the signatures. So if I'm for each hash function there will be a row. Say for the ith row I'll have a slot which I'll call M of I and C, where C is the column, I is the hash function or the row of the min-hash signature that I'm creating. Okay. Now what I'm going to do is I'm going to hash each row, and with each of the, let's again say I have 100 hash functions. So for each of the 100 hash functions, I'm going to hash each row in turn, and I want the slot for I and C to be the hash value of the smallest row in which that column C has a 1. Okay, so and again the idea is that HI of R sort of tells you the order of row R in this random permutation. Except, of course, that there are collisions, but let's not worry about that. Okay, so here's the code. Okay, and again, the outer loop is on the row. Okay, so we're going to, for each row, and the first thing I want to do is compute, let's say, the 100 hash functions once and for all for that row. I don't want to have to do that for every column in which the row has a 1. I want to do it, again, once and for all. And now I'm going to look, again, fixing on row R, in an inner loop. Again, row R is fixed, and I'm going to look at each column in turn. If the column has a 1 in row R, again, if it doesn't have if it has a 0 in row R, forget that column. If it has a 1 in row R, then I'm going to look at each of the hash functions and see if HI of that row R is smaller than the current value for that column and that hash function. Then I will set the hash function, the value of the slot to this smaller hash value. And that way, at the end, M of I and C has the smallest HI of R such that R has a 1 in column C. Okay? Cool. All right. So here's an example Let me see. Okay. I have two hash functions. These are very dopey hash functions. In this case, hi of x will be the row number, will just be x mod 5. So the order of the rows will be second row first, second row, third row, fourth row, fifth row, and then finally. I'm sorry, no. H of 5 is 0, so the last row goes first, then the first row, then the second row, then the third row, then the fourth row. Okay, so that's the first hash function. I only have two hash functions, very short signatures, unrealistically short. G of x is 2x plus 1 mod 5. So it turns out when the second row you get 2x plus 1 is 5, mod 5 is 0, so 2 appears first, row 2 appears first, then row 5, row 3, 1, 2, row 1, and then row 4. In this case, these are perfect hash functions. There actually are no collisions, but again, that doesn't matter. So let's start things off. We'll assume that initially, again, we'll have two signatures. They're signatures of length 2. The rows correspond to the two hash functions. When I look at row 1, but by the way, initially, assume the slots are all infinity. When I hash 1, I get h of 1 is 1, g of 1 is 3. So only column 1 has a 1 in row 1, so I leave the second column alone. It stays at infinity. But I do change, since 1 is less than infinity and 3 is less than infinity, I do put 1 and 3 in the two slots for the first column. Okay, now I'm going to move on to row 2, and here's what I get. Well, these are the hash values, 2 and 0. For row 2, I only have a 1 in column 2, so those two hash values, 2 and 0, get put in the slots for signature 2. Okay, now I go to row 3. Here are the hash values. Now both have a 1, so I can change either. I could change either position to 3, which is h3 of h of 3 is 3. But I already have 1 and 2, and those are smaller than 3, so I leave them alone. But I could also, for g, I could change the value to 2. Well, for the signature 1, I have 3 there. 2 is less than 3, so I do change it to 2. But for the second signature, I have a 0 already, so that's I don't want to change the 0 to a 2. I leave it at the smaller value, which is 0. Then when I go to 4, h and g of 4 are both 4. That's too high. I already have values less than 4 for everywhere. And the only thing, when I do row 5, I could only change column 2 because only it has a 1. Now it turns out h of 5 is 0. I had 2 as the value. 0 is obviously less than 2, so I put a 0 here. For 5, I don't change anything. I can't change anything for signature 1 because there's a 0 there. Okay, so the final signature matrix, I have 1 and 2 for the first column, and 0, 0 for the second column. And so these signatures, 100% disagreement. Again, that's an approximation. If you look at the columns, they do agree in one row out of the 5, so they have a Jaccard similarity of a fifth, but their signatures happen to be all have no similarity whatsoever. Okay, so that's okay. A couple more details. Then I think we're going to take like a 10-minute break in between sessions. I'm not finished with this set of slides yet, but I will catch up. Okay, the interesting thing is that you normally get the data by column, not by row. Okay, so for example, if we're talking about document similarity, the columns of the documents, the rows of the shingles, what you have is for each document a set of shingles, not for each shingle a set of documents in which it appears. So before you do this process, you actually have to sort the matrix by row. Okay. All right, so a 10-minute break, okay? And really, because